let's call it little r, and it would be larger than this, right? Okay, so it would be 1.5 times 10 to 11 meters. Okay? Alright, so that is that. And suppose on Earth we're getting about 1,370 watts per square meter. So on Earth, we get about, let's just say, it's about 1,000. I think this one is for satellites above the Earth. 1,370 watts per square meter. So, okay, watts per square meter. And it says assume the sun has an emissivity of 1. So E is equal to 1. Okay. So the question is find T. By T, I mean the temperature of the sun. At the surface of the sun, right? Okay. So let's see here. Draw a picture. Here's the sun. Here is Earth, somewhere here, right? And the sun is giving off energy in all directions. So the Earth would receive a portion like that. So since this is about radiation, chances are I'm going to use the radiation. So I know that the power radiated, dq dt, would be E sigma times A times the temperature to the fourth. E is 1, or I will not plug in yet. So E sigma. For the area, the surface area of the sun, I have to put 4 pi, the radius, r squared of the sun. So 4 pi, the radius of the sun to the power 2, and then the temperature to the fourth power, right? That's that. So now, so it's radiating this in all directions. How much does the Earth get? We're getting this much per square meter, approximately, right? That much power per square meter. So remember what is this number? What is power over area called? Pressure over area would be.
Pressure area.
Yeah. Intensity. Yeah, it is the intensity. The intensity. It's my boring analogy with I always mention it. A fire hydrant giving off water in every direction. If you're really close to it, you get a lot of spray. You get pretty wet pretty quickly, right? But if you're very far away, you get few sprinkles. Because the farther away, the sphere that encompasses all the water that comes off is growing. It has a larger radius. It has a larger surface area. Right? So the farther away, the less intensity you get. So we're getting this number here. This number is the intensity. Which is the power over area, per unit of area. And the power given off by the sun is this. That's the power. Power is energy per second. Energy per unit of time. That's the power. So it is this. E, so this is power. E sigma 4 pi radius of the sun, and T to the fourth, radius of the sun squared, T to the fourth pi. Divided by area. Area of what? Well, if you draw a line from the sun to the earth, and then make a big sphere. So at this point, all the power from the sun is spread out over a large sphere of this radius from here to there. So how much do you get? Well, per meter, you have to divide by the area of that large sphere. So this would be 4 pi times r squared, where r is the distance from the sun to the earth. Okay. And now we have every number. We can cancel the 4 pi's. They go away. And we can solve for the temperature, right? So I would have this, the temperature to the 4th power would equal to the intensity times R squared divided by E, sigma, and then R sun, like this. And so the temperature would be I R squared over E sigma RS squared, the whole thing to the 1/4 power, right? The 4th root. And now plug in the numbers. So you get the temperature would be, let's see, the intensity 1370, and then R is, what was it again?
1.5.
Squared. And then E is 1, right? And then sigma is this number. Where is that?
Top one.
Over there, 5 point something, 5.67 times 10 to the minus 8. And then the radius of the sun.
6.96.
Thank you. Don't forget to square it. And then to the 1/4 power, or to the 0.25, right? Okay. So you have to plug in the numbers. And so from powers of 10, you should be able to estimate whether you should get hundreds of K, or thousands, or tens of thousands. So we should be able to estimate just from looking at the powers.
Hundreds of thousands.
And then, yeah, it's probably thousands, right? Something for this, probably 40th power, but no.
Going back, so you're reaching that?
Yeah.
If it's negative, you're absorbing?
Yeah. Yes.
Yeah. We got, this is weird, we got 5787.
5787. Yeah, I got 5788.
Oh, okay.
8788. Yeah.
That's the temperature?
At the surface, yeah, yeah.
The surface of the sun?
Can someone touch
So, what should I put?
it? We'll go 5789.
9? Okay. 8 something.
Oh wait, no, 88. What's
88, okay. 88.
Yeah.
Why is the number,
It just seems really low, but it's like, it's a really big surface area, so I mean,
Yeah.
I can understand it.
Professor?
so, the temperature is confirmed by the measurements of the solar spectrum. Yeah.
Can you explain again how intensity is related to the formula, like that correlation?
This,
Yeah.
or this one, right?
Right, because it's I is equal to dq dt technically then, because it replaces it.
I is the power, which is the dq dt divided by the area.
Also, that's what we have in the area.
Yeah.
Oh, okay,
Yeah.
thank you. That makes
So,
sense.
yeah, so in other words, the dq dt is this, is the power, is this one. That is the dq dt. So the sun is giving off energy per second, right? And that energy, it's a set number, that's it. And it's going everywhere, in all directions. The farther away, the less you get per square meter, because you're farther away.
Okay. Also, it's the area, that's the radius, that's where we plug in the radius of distance from sun.
From sun to earth, yeah.
Got it, okay,
Yeah.
thank you, that explains it.
Yeah, so if I were to be here at Earth, and I draw an imaginary sphere from Earth all the way around the sun, I will capture all the energy that comes out from the sun.
Okay, that makes sense.
Yeah, but on Earth, we're only capturing.
Like a small.
Okay. Yeah.
Or you find the temperature at like a closer inside of the sun?
Yeah.
So this would
Well,
only
you can
calculate
estimate
surface
from-
area, right? This would only calculate the temperature at the
The
surface
surface,
area,
yeah.
right? Okay.
Yeah.
How much energy are we absorbing?
From Earth,
Yeah.
it's about 1,000 joules per second per square meter.
Isn't that, that's intensity,
Yeah, W is a watt, right? It's a joule per second. So let's say we're going to set your solar panels, and how much do you get per square meter? So if you want to know how many solar panels you need to put on your roof, you say, okay, every square meter will give me 1370 joules every second, and I consume this much per month. And so you can calculate how many square meters you need based on that. Yeah.
Is this temperature is the surface of the earth,
Of the sun.
of the sun?
Yeah. Michael, yes. And then I will get to.
Can you explain the correlation between the distance and like the area?
The correlation between distance and area? Yeah, so consider a sphere of radius r. It will have a surface area of 4 pi r squared. So the correlation is the area is 4 pi r squared.
Oh, I see. It's like a seg, or I guess like the height doesn't really matter, like the arc length. Like it's just like in the picture behind you, does like the diameter of the earth like matter or no?
The diameter of the earth. Well, if you want how much energy the whole earth gets, yeah, you want to probably know the diameter of the earth or the radius of the earth.
Oh, it's just like 1 point on earth.
Yeah, this is, let's say, if I have 1 square meter on earth, it will get this much.
Okay.
Yeah. I think you had that.
Oh yeah, so this is the temperature like relative to the earth, right? The surface temperature relative to the earth. So would the surface temperature of the sun be hotter if like we're measuring from like Mercury?
No, it's temperature.
So would the radius be like smaller? It would still be the same?
Oh, well, if you go farther away, let's say, this number will be smaller,
Oh, okay.
but
So-
R will be larger, and we will even out, yeah.
The intensity changes.
Yeah, the intensity will change, yeah. The farther away, the less intensity you get. Yeah, Andre?
In the equation, R, capital R is the radius of the Earth, and R's,
Little r?
yeah, little r,
Little r is the distance from Earth to Sun.
and R is the radius of the Sun.
That's the radius of the Sun, yes. I think,
Yeah, if you wanted to know how much, like what the temperature is on Earth from the sun, we would just reverse the area.
It would be so low that the intensity from Earth that it gets to the Sun pretty much negligible.
Right, so like.
But yeah, technically, yeah, you could reverse it.
Oh, yeah, no, like, I mean, like, if
Yeah.
they asked us, like, if the question was like, the sun is emitting this much, power or, heat,
Yeah.
what is the temperature on Earth? How would we solve for that? Would we just change the areas from there, or?
Cause since
I think
the
you're
sun-
saying, let's say somebody's on the Sun and saying we're receiving this much energy from Earth.
No, it's like saying like, I'm standing on this point of Earth,
Yeah.
how much, like, or like, I'm just going out, how much, what's the temperature of the solar panel based on the heat of the sun? I'm not sure if I'm So like, we know the
Well,
temperature
that
of the
would-
sun, and then,
So let's say the solar panel is receiving a certain amount of heat per second, right?
yeah.
Well, then you have to use the heat capacity of the solar panel to figure out how much energy, how much the temperature would change.
Oh, okay, right, so it would
Yeah.
depend on the material, not on the area.
Yeah,
Okay.
yeah, the solar panel would have a certain amount of mass, and its heat capacity and so on.
Oh, so it would be more like a
Q
conduction.
equals to MC delta T.
Okay, got it.
Yeah.
Okay.
Yeah.
No, there's no radius between the sun.
So I'm going to move on to chapter 20. And so let me pause this so that it doesn't mix the two videos together.